Welcome back. In the last video, we coded out this beautiful looking function to pred or make predictions and time them, given a model, given a path of files, given a transform, given a list of class names, and given a target device. And I issued you the challenge of giving it a shot to make some predictions using EffNetB2 and VIT. So I trust you gave that a go, but let's now do it together, hey? 5.2 we're up to. Making and timing predictions with EffNetB2. So again, we're working towards satisfying or running experiments to move towards satisfying our two criteria or seeing which model gets closest. Right now, they're both performing well. Now we're evaluating how fast they go. So let's go back down to here. So how can we do this? Well, let's go here. Make predictions across test dataset with EffNetB2. So I want to go here. Let's test our pred and store function. Two things to note. One, device. So we're going to, let's write this down. We're going to hard code our predictions to happen on CPU, because you won't always be sure of having a GPU when you deploy your model. So unless you set it up explicitly, you might not have access to a CUDA-enabled GPU when you deploy your model, say for example to a mobile device or to the internet. However, there are ways of setting that up. What you should be aware of is that devices with explicit CUDA GPUs are usually larger rather than smaller devices, and they usually cost a bit more. That doesn't mean that you shouldn't ever use a GPU, it's just something to be aware of. And then transforms is that we want to make sure each of the models are predicting on images that have been prepared with the appropriate transforms, e.g. EffNetB2 with EffNetB2 transforms. Otherwise, we'll get disparities in their prediction results. So let's push forward here. We're going to go EffNetB2. We'll create test predicts because our function returns, if we've done it all correctly, it's going to return a list of dictionaries. So let's see it in action, hey? We want pred and store, and the paths we're going to pass in are test data paths, our list of test files, test images. The model we want to use is EffNetB2. The transform we're going to pass in is, of course, EffNetB2 transforms. The class names we're working with are our class names, pizza, steak, sushi. And then finally, the device we're going to use is CPU. And just as per the note above, is hard code predictions to happen on CPU. So you ready? Let's make some predictions with our EffNetB2 feature extractor and time them. 3, 2, 1, no errors. Oh my goodness, here we go. Oh, look at that, it's pretty quick. 8, 7 instances per second, that's pretty good. Now, what's our goal? We want 30 FPS, so ideally this should be up in the 30s, but maybe our model isn't quite there yet. Okay, wonderful. Now, what does this look like? EffNetB2 test predicts. Let's have a look at the first couple. Wonderful. So this is where the list of dictionaries data structure comes in very helpful. You see how we have one dictionary now per prediction. So if we wanted to evaluate each prediction, we've got the exact image path of where that prediction came from. We've got the ground truth class name from here. We've got the prediction probability. We've got the prediction class from our model. We've got how long it took. So is that, have a look, is that close to what we wanted for our goal? What was our original goal? 30 milliseconds latency. So I think that's a bit slower than our latency goal, but we're going to keep pushing forward and evaluate both of our models. So let's turn it into a data frame, hey? So this is why the list of dictionaries is another great data structure. Turn the test pred dicts into a data frame. Oftentimes, whenever I'm evaluating predictions, I like to turn them into a list of dictionaries so I can do this. Import pandas as PD, EffNetB2 test pred df equals pd.dataframe, and I'm going to pass in straight away EffNet test pred dicts. And then pandas, all going well, will turn them into a nicely formatted data frame. Have a go at that. Beautiful. So there's our image path. There's our class name, prediction probability, pred class, time for each prediction, and whether it was correct or not. So this is one of the main reasons, again, if we go back to our function, that we hard-coded a few of the things to be on the CPU, because pandas works on the CPU rather than on the GPU. So although our function is device agnostic, if we want to evaluate our prediction dictionaries later on, we make sure that the information that's stored in them is back to the CPU. Otherwise, we'll get errors when we try to use our EffNetB2 test pred dicts variable with something like pandas or matplotlib or numpy. So that's where we put it back to the CPU. Now, we can inspect on this data frame if we wanted to. We can check the number of correct predictions. This is again why the list of dictionaries is such a helpful data structure. So let's check the correct column. This is the correct column over here. Let's see how many were correct. Value counts. Well, it got 145 out of 150 total, so it got 5 wrong. And that's pretty in line with the results we got way back up here for our EffNetB2 model. We got, what did we end up with? About 97% test accuracy. That's pretty aligned with it. Let's see how long it took. I was going to challenge you to do the same thing for VIT, but we haven't done the thing we wanted to do yet. I'm getting ahead of myself here. Find the average time per prediction. So EffNetB2, average time per pred equals, this is where we can use our data frame as well, EffNetB2 test pred df dot time for pred. So we're indexing onto this column, and now let's get the mean of that column, and we want to round that to 4 should be enough. So now let's print this out. We'll go EffNetB2 average time per prediction, and what do we think it's going to be? Is it going to be near our goal of real time? Oh, okay. So it's about 120 milliseconds per image. So it's about 3 to 4x higher than our goal of 0.03 seconds. So, Now, a thing to keep in mind here as well is that that's not necessarily bad. We can still build a deployed model, but I'm going to write a note here. Is that note, prediction times will vary, much like training times, depending on the hardware you're using. So generally, the faster your compute, e.g. CPU or GPU, the faster the predictions will happen. So we're running on a Google Colab CPU right now. Now, I'm not exactly sure what type of CPU it's using, but just for some context, if we go into book version of what we're working through, and we go to making predictions with EffNetB2 5.2, these are the results I got on my local PC. So I have a deep learning PC, which has some pretty advanced computer chips in it, such as an Intel i9, and my average prediction time with EffNetB2 was around 0.31 seconds. So just under real time, what our goal was. But on Google Colab, again, I'm not sure what hardware Google Colab uses, but it looks like it might be an Intel Xeon XR or something like that. What's the hardware spec for Google Collaboratory? You can check into that. But I got an average time of 0.1396 seconds, so 3 to 4x slower, which is reflective of what we got here. So don't worry again if your value here is not exactly these numbers, but you might have done something wrong if it's like 10x this number or 3x, or if it's faster, hey, run with that. That's a really good thing. But now we've got the EffNetB2 average time per pred. How about we do the exact same thing, but for our VIT feature extractor? So that's going to be my challenge to you before the next video, is to take the VIT feature extractor and go through the steps we did in 5.2, except for instead of EffNetB2, use VIT, and just make sure to use the VIT transforms as well. And see what's the time for the average prediction for our VIT and compare that to EffNetB2. So give that a shot and we'll do it together in the next video.